Welcome back, everybody. This week, we're going to be talking about climate models. So our goals for this lesson are for you to be able to explain what climate models can and can't tell us about the climate, and to be able to use some basic climate models to examine future climate. So let's start with a very basic question. What is a model? And in talking about models, I always like to refer to this quote by the mathematician George E.P. Box. He said, "All models are wrong, but some are useful." So it's important to keep in mind that a model is not a perfect representation of the world, right? So every model is wrong. Every model is not exactly matching reality, but models can be very useful. They can help us to understand reality. They can help us to understand key things that are happening in our world. You can think of it as similar to what we said about maps way back at the beginning of the class, right? Every map is going to simplify and distort things about the Earth. No map is going to perfectly represent everything there is on the Earth, but we can make a map in a way that's useful, that helps us to understand the Earth, despite not being exactly the same as what is there in reality. So a model, for the purposes of our lesson here, is a mathematical representation of the processes making up the climate system. So we have some understanding so far of some of these key processes that shape our Earth's climate system. And if we represent them mathematically, so we don't just say that, for example, when air gets warmer, it can hold more moisture, but we actually put in the numbers for, well, exactly how much more moisture is the air holding for each degree that it gets warmer, right? We put actual numbers to it so that we can say how much is actually happening in these processes. Then we can more accurately represent everything that is going on in the climate system. So we have a mathematical representation of the system, and then we can do things with that mathematical representation. We can test out ideas. We can make predictions. We can examine the interactions of different parts of the climate system by seeing how they're going to affect each other within the model. And a model is always in conversation with observational data. So all of the data that we were talking about in the last lesson, all the facts that we have observed about our Earth, feed into our model. So we use that data to create our models, to help us to understand what kinds of things should we be building into our model, and what are the mathematical relationships that we need to encode into the model. And then we also use that data to check the outputs of the model to see if what the model is telling us matches what we can see in reality. And if it does, that shows us that our model is probably onto something. If there's a significant difference between what the model says and what we see in reality, then we know that there must be something more going on that we're leaving out of our model, that our model is missing the mark in some way, that the model is not useful, to go back to the George Box quote there. So how do we model the atmosphere? There are two approaches that we might take to build a model of our atmosphere to understand what's happening with the climate. So one approach is what we call a physics-based model. So the numbers in our model represent physical processes. So climate science is in some ways just applied physics, right? These are all aspects of physics that help us understand what the atmosphere is doing. And so we have figured out certain key relationships based on the physics of how the atmosphere works, how air moves, how energy interacts with our atmospheric system. So things that we've been talking about, like the relationship of how much moisture can be held in air at different temperatures, right? That's a physics fact that we can build into our model. About the albedos of different surfaces, right? That's a physics fact that we can build into our model. About the interactions of different kinds of gases with energy. It's a physics fact that we can build into our model. And so if we can put all these physics facts together, then if we're doing it right, if we've got all these these facts correct and we've got it, all the right ones put into the model, then the result should be that it should replicate the patterns that we see with our global climate system, that we can build up from these basic physics relationships to see something that looks like the climate system that we actually see. So that would be a physics-based model where the guts of the model are mathematical relationships between different variables that we have established based on physics. The other way we might approach modeling the atmosphere is a statistics-based model. So in this case, our numbers are describing the climate patterns that we can see. So we can see certain things happening with our global climate, differences between climates in different places, how climate changes over time. Right? We've got those numbers to be able to describe those patterns, and we can then statistically predict which patterns will lead to which other patterns. So we know that we have a certain pattern distribution of temperatures, and that tends to be followed by a certain other distribution of temperatures. So we can statistically link one thing to the next to be able to predict the future climate patterns from the ones that we have data on from the past. So we're not digging into the nitty-gritty of how it all works, which is what a physics-based model would do. All right, physics-based model is based on trying to understand how these things work. Why does this happen? Statistics-based model is just trying to predict, based on our observations, what tends to follow from what. And so these days, there's a ton of work being done using LLMs, large language models, to improve our statistics-based climate models. And so you may be recognizing that my description of these statistics-based models probably sounds a lot like how I described generative AI that's based on LLMs, right? If you are talking to ChatGPT doesn't understand anything about the world, right? It doesn't know what your words mean. It doesn't know anything about the world that you're talking about when you type stuff into it. All it knows is that in its training data, certain sets of words tend statistically to be likely to be followed by certain other words. And so if you type into ChatGPT, hey, it's my birthday today, then the system can recognize that one person saying it's my birthday statistically is likely to be followed by someone else saying happy birthday, and so ChatGPT will reply happy birthday, right? That's the basic idea of what's happening within a large language model, and so we can apply that same thing to the climate system, that if we've got all this data on temperatures and wind patterns and precipitation and stuff from around the world, we can feed that into an LLM and it can predict what it will look like next based on what usually follows from what in that training data. So two different approaches, and we've got people working on both kinds of models, and the results of one kind of model can help us work on improving the other kind of model. This is not a situation where one's a good kind of model and one's a bad kind of model. They both have important roles to play. So they are both useful in different ways, even though neither of them is precisely true. Neither of them is exactly matching every little thing that happens on the world, but they're both useful in helping us to see what's going to happen with our global climate. So within either of these categories of models, we can examine an individual model because there are tons of climate models out there. Different people have developed different ones that are built differently for different purposes. But looking at kind of the basic specs of a climate model, some of the key things we want to look at are first the spatial scale and resolution. So spatial, remember, means relating to geographical space, where things are. So the spatial scale is how big of an area does the model cover. So the models that we're going to be looking at in this unit are generally global models. So the scale of the model is the entire Earth. There are models with a more limited scale. So there are regional climate models that people have developed that are going to focus on just the climate of North America and not worry about what's happening around the rest of the world. So the scale is how much of the Earth does our model cover. Spatial resolution is how much detail can we get. Right? Are we going to be able to look at just sort of very broad processes, or are we going to get down to very fine place-to-place differences, right? You can think of this as the difference between a high-resolution photo that has very sharp detail. You can see a lot of very small things if you zoom in on it, versus a low-resolution photo is kind of blurry, might be very pixelated. Same thing with our climate models. They can have very high spatial resolution so that they are seeing a lot of details that are happening over very short areas of the Earth, or they can have very coarse spatial resolution where they're only looking at the big picture of very large processes. Likewise, we can talk about temporal scale and resolution. So temporal means having to do with time. So temporal scale, how long of a time period is our model looking at? So we have some climate models that are designed for analyzing paleoclimate, the ancient climates of our Earth, that might have a scale of hundreds of millions of years. We're trying to understand changes in climate during the Carboniferous period 300,000 years ago, or sorry, 300 million years ago. Right? We need that very large temporal scale. Others are much more limited temporal scale. They may be trying to look at what happens over the course of just a few decades. And then temporal resolution. Are we looking at this on a year-by-year basis? Are we looking month to month, day to day, hour to hour? Right? How finely can we slice the time within our model? That's our temporal resolution. And then third, we can talk about what are the variables and parameters that this model incorporates. So these are all of the things that the model can say something about. What aspects of the climate system are incorporated into the model, and which of those are incorporated as variables and which are incorporated as parameters. So a parameter is like a constant. So if you think about a mathematical equation, right, in algebra, you have some things that are variables, right? You've got x equals whatever, y equals whatever, right? Those are variables. You could put different numbers into that variable and get different sorts of results. Other things are constants, right? You've got a 4 in your equation. That's a 4. That's just going to always be a 4. A parameter is like a constant. It's something that does not change. It's an aspect of the system that we're treating as constant. So on the one hand, pretty much every climate model is going to treat temperature as a variable. Right? Temperature is going to change, the different temperatures in different places, different temperatures over time. So that's pretty much always going to be a variable. On the other hand, something that's going to be a parameter in pretty much every climate model is the shape of the Earth. Right? So our climate models have to incorporate the fact that the Earth is round, is pretty close to being a sphere. And that's going to be a parameter. That's not going to be something that is going to change within the model, because that's not something that changes in real life, right? The shape of the Earth has been the same basically since the Earth first formed, and will continue to be the same into the foreseeable future. So we don't treat the shape of the Earth as something that might change within our model. We treat it as a parameter. Parameter, we're working with a spherical Earth for our model. But then in between there are other things that might be a variable in one model and a parameter in another, just depending on what it is you're trying to investigate using this model. Sometimes it's convenient to hold certain things constant, treat them as parameters. Other times it's useful to treat them as variables, as things that might change during the course of running your model. And so that helps us to understand the difference between weather models and climate models. So both of these are models of the Earth's atmosphere, but they are useful for very different purposes. And so therefore they are built differently, and they have different scale and resolution and different variables and parameters put into them. So one thing that weather models tend to really emphasize is having very fine spatial and temporal resolution. I have scales on the slide there, I should say resolution. So if you think about the weather report, if you looked up a weather report recently, they tend to have very fine temporal scale. Temporal resolution. So you get your forecast that will tell you, oh, the rain's supposed to start at 7 o'clock tonight. Right, so it breaks it down hour by hour. So it's got a very fine temporal resolution. It also tends to have very fine spatial resolution. So you have slightly different weather forecasts generated for, say, Slippery Rock versus Harrisville versus Prospect. Right? Each little town gets its own weather forecast because the models incorporate little things like, some towns are a little farther north or a little farther south than others. Some are a little higher in elevation than others, etc. So that will give you slightly different forecasts for slightly different places. So weather models are prioritizing this very fine resolution in both space and time. But then they're also parameterizing, that is, treating things as parameters that might happen over larger scales of space and time that are going to be very important in a climate model context. So, for example, weather models tend to parameterize the concentration of greenhouse gases in the atmosphere. So a weather model treats the composition of the atmosphere as basically static, as the same, because the composition of the atmosphere, the percentage of the atmosphere that's CO2, is not going to change in any meaningful way just from today until the end of the week. Right? It's not going to change in any noticeable way just over that short period of time, which is what we're trying to predict with our weather model. So the weather model is not going to incorporate changes in CO2 concentration as a variable. That's just going to be held constant in the weather model. But of course, with a climate model, if we're trying to understand what's going to be happening 100 years from now, then we definitely want CO2 concentration to be a variable because we know that's going to change. Right? We know that we're going to have a different amount of CO2 in the atmosphere 100 years from now than we have right now. So that needs to be something that can change in the course of running our model for examining temperatures or examining climate over a century, whereas it's something that we don't need as a variable that's not going to change over the course of making a weekly weather forecast. So that means that we use different models for modeling climate and modeling weather. We can't just take a weather model and run it for a very long time to look at future climate. Okay, so let's dig in a little bit more on the issue of spatial resolution so you can see how this gets incorporated into our climate models. So climate models tend to divide the Earth into what are called voxels, which is volume pixels, right? You're familiar with pixels in like a photo, or the little squares. So if you are doing 3 dimensions, then those squares become little cubes, and we call those voxels, volume pixels. And so for each climate variable that we have, right, things like temperature and humidity, wind speed and direction, all these different variables that we're interested in examining, each voxel has one value for that. Just like in a photograph, each pixel has one value for the color of that pixel. So that means that the finer our resolution, the smaller our voxels are, and therefore the more voxels we have, the more detail we can get with these processes. Right? We can break down our average temperature over a large voxel into the variations that might exist if we break that into smaller voxels. And you can see in the diagram there how the spatial resolution of the climate models changed over the course of the first 4 IPCC reports. So later in the semester, we're going to talk about the IPCC, the Intergovernmental Panel on Climate Change. It's kind of a global organization that puts out these big reports that summarize the state of climate science. And so in the first report that they did, the first time they did one of these reports, their models used voxels that were 500 kilometers to a side. So each of those little blocks you see under FAR, the first assessment report, is 500 kilometers square. For the second assessment report, they improved the resolution to 250 kilometers to a side. So they basically took each of those voxels and split it in half in each direction. Third assessment report, they got it down to 180 kilometers to a side. AR4, the fourth assessment report, 110 kilometers per side. So they are increasing the spatial resolution, and you can kind of see on those illustrations there. The first one, you might look at that and you have no idea what part of the Earth that's supposed to be. By the time you get to the last one, it's pretty recognizably Europe on the diagram there. So we're getting a lot more detail that we can do when we have those smaller voxels, but that comes at the cost of increased amount of computational power that it takes to run the model. So if you take a voxel and cut its sides in half, so you're making it half as big in all 3 dimensions, you're going to end up turning one voxel into 8 voxels, right? You're just splitting it 3 ways. You're turning 1 into 8. And so you're going to get 8 times as many voxels. That means it's going to take 8 times as much computing power to run these models. And these models are enormous. They are not something that you can run on your desktop computer. They're something that you have to get take time on supercomputers to run these models. So for high-level climate science, there is a trade-off between how quickly you can run the model and how much spatial and temporal detail your model can do. Now, in our lesson, we're going to look at some super simple climate models that are designed to run on your computer, but those are not the kind of models that go into the work of professional climate scientists and the IPCC reports. Okay, so if we've set up our model, we want to make sure that our model is accurately representing what goes on the Earth. And so one of the key ways that we check the accuracy of our models is through something called hindcasting. So you're familiar with forecasting, trying to predict the future, going forward from where you are in time. But before we trust a model to forecast the future, we want to make sure that it can hindcast. That is, it can predict the past behind us. So we basically take our model and we feed into it starting parameters from some point in the past, and then we try to use the model to predict what happens between then and now, the present, because that's a period of time that we have actual data for. So then we can compare what the model does over that time period to what the actual data was, what actually happened on the Earth, and we can see if the model is matching up well to the real data. So when we do this, we don't just run the model once. We run the model a whole bunch of times, sometimes hundreds of times, because all of these models have some probabilistic element. So there are some things where there's, if X happens, then there's a certain chance that Y will happen after that. It's not a guarantee X always leads to Y. There's a chance that, 30% of the time X leads to Y. So there's this probabilistic element to it. So what we generally do is we run the model a whole bunch of times and then take the average of all of those runs. So that will even out those probabilistic elements. It will even out the 30% of the time that Y happened and the 70% that it didn't happen. So when you're looking at model results from climate models, you'll often see them represented as kind of a wide stripe. And that represents the range of all of the model runs. And then they'll often put then a darker line down the middle that represents the average from all of those model runs. And so that's what you're seeing on the graph here. So this is a graph from hindcasting the 20th century using climate models. So we started off our models with data from 1900, and we ran the models to try to predict what happened between then and 2010. So all of the yellow lines on this graph are the individual model runs. So each individual time we ran this model, I think this was based on 100 model runs. So each of those 100 is its own little yellow line there. Then the thicker red line is the average from all of those model runs. So you can see it's following down kind of the center of where those yellow lines are clustered. And so the red is our average from, I think this is 100 model runs of trying to see if we can predict the climate over the course of the 20th century into the beginning of the 21st. The black line represents our actual observations. Now, I should say this is all temperature anomalies that you're seeing on this graph. You may have recognized the shape of this from working with the temperature anomaly data in your activity from last week. So you can see that the red and the black pretty well match each other. They tend to follow the same route. The red is lying within the ups and downs of the black throughout this. So we're able to successfully hindcast here. We were able to match the overall trend, the overall upward trajectory of our temperatures over this period of time. We're able to predict the final temperature there in 2010 pretty close to accurately, right? The red and the black are very close together at the end. There, we're also able to match the ups and downs along the way up to a pretty good degree, right? So you may recognize some of those general ups and downs, again, from your exercise working with the temperature anomaly data. And so the hindcast was able to follow those ups and downs. And the hindcast was even able to accurately reflect the impact of volcanic eruptions. So on this particular graph, you can see there are those vertical lines there that are labeled. These are 4 of the biggest volcanic eruptions that happened during this time period. And if you recall our volcanoes lesson, we said that volcanoes produce a lot of CO2. So in the long run, volcanoes have a warming effect on the atmosphere because they're adding greenhouse gases. But volcanoes also produce a whole lot of aerosols. They produce a whole lot of tiny little particles that go into the atmosphere and increase the Earth's albedo. So they reflect more of the sun's light away. And so that means that they have a short-term cooling effect. Okay, so a volcanic eruption will cause cooling in the Earth's temperature for a year or two after that eruption happens because of all the aerosols that it puts into the atmosphere. But then after a few years, those aerosols get kind of washed out of the atmosphere and their influence goes away. And so what you can see on the graph here is that both the actual observed temperatures, or the real data, and the predicted temperatures from the model dip sharply but briefly after each of these major volcanic eruptions. So that shows our models are accurately reproducing the response of our global temperature to volcanic eruptions. So that's one element within the model that is very clearly shown to be working well when we do this hindcast to test what the model is doing. So if the model does a good job of hindcasting, if it's able to predict things that we already know the data for, then that gives us confidence that we can forecast with the model, that we can take this model, give it today's data, and have it project the future. So in order to do that, we do have one important complication. When we were hindcasting, we could feed into that model the information that we know about things like the amount of greenhouse gas emissions that happened over the course of the 20th century. Right? We have definite data about that. We know how much greenhouse gases we emitted during that time period. So we could just feed that directly into the model. If we're predicting the future, we don't have that data. We don't know exactly how much greenhouse gases we're going to emit. And in fact, we're often hoping that our model results persuade people to change how much greenhouse gases we're emitting. Right? If our model can say that, well, if you emit this much greenhouse gases, it will have these effects on the Earth, somebody might say, oh my gosh, I don't want that to happen. We're going to emit fewer greenhouse gases. Or maybe the model says, well, if you emit this much greenhouse gases, this bad thing won't really happen. And then somebody will say, well, all right, we're going to go ahead and emit that. Right? We might change what we're going to do in response to the model results. So we can't predict exactly what our future greenhouse gas emissions are going to be because it depends so much on what people choose to do. So human activity is incredibly hard to predict. And so people will sometimes say that the social sciences are actually much more difficult than natural sciences. Because if I want to predict, say, the effect of changes in solar radiation on the climate system, I can do that to a very high degree of accuracy far out into the future, because the physics processes that shape the output of energy from the sun are very predictable. They're not going to change based on the predictions I make. The sun's not going to hear what I have to say and decide to change how much radiation is coming out. It's just going to be an evolution that we can predict of all the nuclear reactions going on in the sun. Whereas if I'm trying to predict what choices are going to be made by political leaders and businesses and consumers and activist groups and everybody else that has an influence on things like how much greenhouse gases are being emitted by human activity, that is incredibly difficult to do in a reliable way. Again, especially because people might hear my predictions and change their behavior based on the predictions. So predicting things in the social sciences is incredibly difficult. So what we generally do, rather than trying to predict one set of numbers of how much greenhouse gases are going to be emitted in each year in the future, we construct a range of scenarios. So we have several different scenarios that we look at, and we can compare those scenarios. So it creates kind of an if-then situation. We can say, if you do X, then Y will happen. If you do Z, then A will happen. If you do B, then C will happen. Right? We can set up an if-then kind of situation based on different things that people might choose to do, because we can't predict exactly what people are going to do, but we have some ideas about the range of things that might happen. Right? It's totally unrealistic to expect that everyone is just going to turn the tap off and completely stop emitting all greenhouse gases tomorrow. So that's not a scenario we need to worry about, not a scenario we need to model out. But there are, a range of things, some involving less emissions, some involving more emissions, that do seem within the realm of possibility. So that can constitute our scenarios. So how do we put these scenarios together? Well, we have two different approaches that we might take, bottom up and top down. So a bottom up scenario, we start by creating a range of plausible stories about what people might do in the future, right? So if you're imagining, kind of like you're a science fiction writer, trying to imagine what might people end up doing in the future. Maybe you have one very optimistic scenario where, people become very educated about climate change and they realize the negative effects, but then also we develop a bunch of new technologies very quickly that help us to do things without emitting so much greenhouse gases, and so we reduce our emissions very quickly. Right? That might be one scenario. That's one thing that might happen. That's a plausible future. Right? You could write a science fiction story about that future, and people wouldn't dismiss it as being ridiculous. On the other hand, you could construct a very pessimistic scenario where people kind of stick their head in the sand and don't want to care about climate change and would rather drive their gas-guzzling cars around more, and politicians around the world are fighting with each other and can't come to any agreements, and so we end up with very high emissions going into the future. Right? That's a plausible scenario. That's a thing that we can imagine happening. It's something that is clearly within the range of possibility. So we create a range of these different stories about how the future might go. Then for each story, we try to estimate how much greenhouse gas emissions that would be produced if we followed that story. So if we follow the story where everybody gets educated and becomes very concerned about climate change, then what would that do to people's behavior? What kind of laws might get passed in that scenario? What kind of choices might be made by businesses? And what would the result be in terms of the emissions that would be produced? And then likewise, take our pessimistic scenario and think, well, if people do that, if that story plays out, how much emissions are we going to be seeing in that scenario? So then we build a set of greenhouse gas concentrations for each time period, right? So if we're on a year-to-year basis, we might think, okay, for each year, how much greenhouse gases would be emitted by people in each of these scenarios. And then we can use the greenhouse gas estimates to calculate the radiative forcings, right? So we know that if we put X amount of CO2 into the atmosphere, it's going to have a certain radiative forcing, right? If you remember back to last week's lesson, we can calculate from amounts of greenhouse gases into the atmosphere what impact that's going to have on the Earth's energy balance. That's our radiative forcing from that greenhouse gas. So we can then get the radiative forcings, and the radiative forcings are what we then feed into our model to see what's going to change about things like global temperatures. And then similar kind of thing would happen with other variables that we have in our model, right? So we'd use those same scenarios to predict changes in land cover that would change the albedo, for example. So that's one way that we can build the scenarios. We can, put ourselves in this kind of science fiction writer role and try to envision things that might happen in the future. The other approach we might take is a top-down scenario. So with a top-down scenario, we start by selecting a range of radiative forcings that we're interested in examining. So we want to understand what would happen if we had a certain amount of radiative forcing. We might pick a really high one that would lead to very significant climate changes. We might pick some very low ones that lead to very little climate change, and some in between. So we start by picking out some radiative forcings we're interested in examining. Then for each of those, we come up with a plausible set of greenhouse gas emissions that would produce that forcing. So if we are interested in saying, what would happen to the Earth if we got a radiative forcing of 4 watts per square meter by the year 2100, then, well, how could we get there? What kind of greenhouse gas emissions that are sort of plausible that humans could create would lead to that radiative forcing? So we're basically doing the calculations backwards from what we did in step 3 of the bottom-up scenarios. So then we get those sets of greenhouse gas emissions, and then we think about, well, what might people do that would produce that amount of greenhouse gases? So we know that we're going to produce X amount of CO2 this year, and then X amount the next year, and this amount the next year. Well, how would we do that? What kind of policies might be adopted to lead society to follow that trajectory? What kind of choices by voters and consumers might lead to that trajectory, etc. So we're basically doing this in the reverse order. So bottom up and top down. And this is another case. Neither one of these is inherently superior to the other. They're each useful for different kinds of applications. And in your exercise, you're going to be exploring both bottom up and top down scenarios in a simplified climate model. So some of the scenarios you're going to be looking at are ones that have been used in those IPCC reports. So these big reports that are summarizing the state of climate science. So we have these bottom-up scenarios, and you can see from this diagram how they're constructing these stories about the future. So, for example, the A1 scenario here, they're saying, okay, let's imagine a future in which global population peaks in mid-century and declines. There's very rapid economic growth, rapid introduction of new and more efficient technologies, convergence among regions with a reduction in regional differences in per capita income. So that's, right now we have a lot of global inequality, right? Some very poor countries, some very rich countries. They're saying for scenario E1 or A1, we're imagining that there's, an equalization there, that the rich countries don't continue getting far, far richer and the poorer countries catch up somewhat. So we reduce that global inequality, right? So those are all things that are plausible to imagine happening in the future. Depending on how pessimistic you are, you may be confident in those kind of things happening, or you may be not so confident that that's likely to happen. But it's a thing that, we can imagine those things happening. They're within the realm of possibility. And then from that, you can say, okay, well, if that happened, what would that do to our emissions, right? So if global population peaks in mid-century, that's going to have an effect on our emissions, right? Because all else being equal, the more people you have, the more emissions you have, because each person is going to drive their car around and, need food produced for their consumption, et cetera. Right? Rapid economic growth. Well, we know something about the relationship between economic growth and emissions of greenhouse gases, right? That typically when the economy fires up, we get more emissions because people are making more stuff, burning more fuel, using more energy. But then on the other hand, that scenario says rapid introduction of new and more efficient technologies. So if we have more efficient technologies, that means that that's going to lower the emissions. We're going to be able to do more for our economy with producing less emissions if we have better technology, right? If we swap out our gas cars for electric cars, for example. Right? So you can see how you take all of these ideas about what might happen in the future to build out an idea of what kind of greenhouse gas emissions might that result in, and then from that you can calculate your radiative forcings. Then the other scenarios shown here are just different stories we might tell about the future. So if we go to the other end there, the B2 scenario, so there, rather than population peaking in mid-century, the B2 scenarios, well, what if we have a continuously increasing global population? The population just continues to grow throughout the coming century. We have intermediate levels of economic development. So we have less economic growth in B2 than we had in A1. We also have less rapid technological change in B2 than we have in A1. So again, these are all things that are plausible. We can imagine that that might be our future, and then we can figure out, well, what impact would that have on greenhouse gas emissions and therefore on our radiative forcing. So that is how we might build bottom-up scenarios. We also can build some top-down scenarios. And so these are the ones being used in the latest IPCC report. They're referred to as representative concentration pathways. So if you see that RCP, that's representative concentration pathway, that means it's a top-down scenario. And so each of these is RCP some number. That number is the radiative forcing due to human activity in the year 2100 in watts per square meter. So the RCP 8.5 is a scenario in which we reach an additional 8.5 watts per square meter radiative forcing by 2100. The RCP 2.6 is one where we only get 2.6 watts per square meter of radiative forcing by 2100. So these are scenarios that go from our current situation to this point in the future where we have a particular radiative forcing. And then on this chart is showing the CO2 equivalent. So that is the amount of carbon dioxide plus all of the other greenhouse gases times their global warming potential, right? So we're converting, X amount of methane. Well, that's equivalent to 28 times that amount of CO2. So we convert everything into terms of carbon dioxide so that we can have a single number there. So we can see, in order to get to 8.5 watts per meter squared radiative forcing by 2100, what amount of CO2 would need to be emitted over the course of the century to get there, and likewise for the other RCPs, representative concentration pathways. So this is showing you that that second step of taking our target of radiative forcing and calculating how we would need to get there in terms of the greenhouse gases we emitted. And then the third step would be to take one of these pathways and try to figure out, well, what kind of policies being adopted by countries, by global institutions might put us on that trajectory? What kind of choices being made by businesses might put us on that trajectory, etc. So starting with starting with the amount of energy and working backwards to what is actually going to happen to get there. So once we have these scenarios, then we can now forecast. We can put different scenarios into our climate model and project forward to see what the model says is going to happen in the future. So on the upper graph there, you can see average global surface temperature being projected out to 2100 based on the different RCP scenarios there. So the graph is showing just the highest and lowest one there. All right, so if we follow that RCP 8.5 scenario, where by 2100 we have a radiative forcing of 8.5 watts per square meter, you can see that that is projected to lead to an increase in global temperature of about 4 degrees Celsius. So that's where the average, the dark line in the middle is, but then you can see there's also a range. Okay, so different model runs were a little higher, a little lower than that, so the range spans, looks like from about 3 to about 5.5 degrees, right, is the range, with the average being at about 4 degrees Celsius. And then if you look at the lowest one there, RCP 2.6, so if we end up with 2.6 watts per square meter of radiative forcing by 2100, according to that scenario, we would expect to see about about 1 degree of warming, with a range kind of from a little less than half to almost 2 degrees of warming. So that's what our model is telling us is likely to happen in the future if we were to follow each of those scenarios, and then the other two scenarios fall kind of in the middle there. So they took them off the graph to make it easier to see what's going on. So our current best models are predicting average temperature anomalies in 2100 of a range from about 1 to 4 degrees Celsius, depending on which scenario we're looking at. And the lower emissions scenarios that we see here are likely already out of reach. So we are probably not likely to hit that RCP 2.6 scenario because these calculations were made some years ago, and so we have already blown past the emissions that were projected according to that scenario. So we're looking at something maybe closer to some of the higher scenarios. So that's predicting temperature. We can also use these models to predict other aspects of the global climate system. So in the lower graph, you see mean sea level rise. So sea level rise is one of our effects that we expect to see from climate change. We talked about the basic idea behind sea level rise in a previous lesson, but with a climate model, we can actually predict exactly how much sea level rise do we expect to see, right? How much higher will the average global sea level get under different scenarios? And so there you can see, again, there's a range of uncertainty because there's a probabilistic element in these models, but according to the averages there, right, when we average all the model runs for a given scenario, you can see that the RCP 8.5 shows almost 0.8 meters of sea level rise by 2100, and the 2.6 shows that we're a little over 0.4 meters of sea level rise by 2100. So we can use these models to predict not just global temperature, but we can predict specific effects of climate change, things like sea level rise that we expect to see as a result of climate change. Those projections of future temperature, future sea level rise, we're looking at the global average, right? What's the global average sea level rise across the entire Earth? But our most sophisticated climate models can break things down geographically. We can look at the different impacts that we might have from climate change in different parts of the world. So this figure here comes from that latest IPCC report, and you can see here they're looking at scenarios that result in different levels of climate change, so different numbers of degrees of warming, and then they're looking at several different factors that are going to have different outcomes in different parts of the world. So the first set of maps there is looking at temperature changes. And so we can see, on the one hand, of course, the hotter the world overall gets, the hotter the things get in every different part of the world, right? We're not seeing any cooling projected there, but we can also see that there are spatial differences that arise. So, for example, in general, we find the polar regions, especially the Arctic, warming the fastest. So some of the biggest temperature changes that are being predicted in any given scenario are being seen in the Arctic area. We're seeing somewhat less temperature increase in some of the tropical areas, right? So that single number of this many degrees Celsius of warming hides a lot of geographical variability. So even if the world as a whole has gotten 4 degrees Celsius warmer, the Arctic may have gotten 7 or 8 degrees Celsius warmer. So have warmed a lot more than that average, and then there are going to be other areas that have warmed less than that global average. Second row of maps there is looking at soil moisture change. So this is how much moisture is in the soil. This is a critical factor for agriculture, and it also gives us a sense of areas getting wetter or drier. So you can see there are some parts of the Earth that are expected to get drier as a result of climate change. Other areas are expected to get wetter. So for example, the southwest of the United States is expected to get drier as a result of climate change, whereas, say, the Sahara in Africa is expected to get wetter. India is expected to get wetter. The Amazon is expected to get drier. So we can examine changes in precipitation and retention of moisture in soils in different areas, because that's one that we're not seeing this overall trajectory of change on the Earth. So if we were only looking at that global average we would think that changes in soil moisture are not going to be a big deal because it's not going to change very much. But in fact, what we're seeing is that some areas are going to get much wetter, some areas are going to get much drier, and either of those could be a problem. Obviously, dry soils is going to make it hard for crops to grow because they can't get that moisture that they need for their growth. Things getting much wetter can also have detrimental impacts on crop growth because if it gets too waterlogged, probably some of you have had the experience, if you water your plants too much, they die just like if you don't water them enough. And so both of those situations can have significant but different kinds of negative effects. So our most complex models can differentiate the impacts in different parts of the world. So where one area might experience one impact from climate change, another area might experience a different impact. So our different types of models give us different levels of complexity for understanding the Earth. And if we think back to the George Box quote, different models are useful for different things. So our simplest kinds of models are what we call energy balance models. So this is a calculation based on energy in, energy out. So if you remember the Stefan-Boltzmann equation, right, where we could connect the amount of incoming solar radiation to the albedo and temperature of the Earth, that was an extremely simple energy balance model. It's probably the simplest possible energy balance model that we could put together for the Earth, just that one little equation. But then we can start adding factors to that. So in our lecture, we saw that the Stefan-Boltzmann equation was not giving us a good idea of the surface temperature of the Earth because it wasn't accounting for some critical things like the effect of the atmosphere in trapping some of that energy. So we can start adding terms to that equation, making it more complex in order to capture additional processes that are happening on the Earth. Eventually, as our complexity increases, we get to what we call Earth models of intermediate complexity, or EMICs. So these are models that start to incorporate space and time elements. So if we think about that Stefan-Boltzmann equation, it didn't incorporate time. It was just telling us what the equilibrium would be. If we had this much insolation and this much albedo of the Earth, what would the temperature of the Earth end up being? But of course, the Earth doesn't respond instantly to changes in albedo or insolation. It might take some time to readjust and to reach this new temperature. Likewise, that is just giving us one number for the entire Earth, right? It's our average temperature for the whole Earth. But we know that things happen differently in different parts of the Earth. So if we start to differentiate what happens in different places on the Earth, and we start to look at how much time these processes take, we are in the realm of Earth models of intermediate complexity. The most complex models we have, the ones that were used to generate those forecasts that we've been looking at, are what are called general circulation models, or GCMs. So general circulation models are our most complex type of climate model. And the picture there shows a representation of kind of conceptually what's going on within a GCM. Obviously, this is actually just represented as a long series of mathematical equations, but you can see some of the processes that a GCM is trying to capture. They're looking at the radiation coming in and out. They're looking at the circulation of the atmosphere. So the air that is in one voxel is going to flow into another voxel over time as a result of wind. We're looking at exchanges of gases between different parts of the Earth's system. So if you remember your carbon cycle, right? We have things like absorption of CO2 into the oceans and outgassing of CO2 back out of the ocean. That's something that a GCM is going to try to account for because that's going to alter the balance of CO2 in the atmosphere and therefore the amount of greenhouse effect that we get. A GCM is going to try to account for ice sheets on land and in the ocean and the effects of those on the albedo of the Earth and on other processes that are happening and how that interacts with changes in things like temperature. We're looking at vegetation, right? So the biosphere gets incorporated into GCMs because we saw the biosphere as part of our carbon cycle. So what happens to plants and animals on our Earth, how much carbon they're taking up and letting out, and how that's going to change, as they respond to changes in things like precipitation and temperature that make it possible for certain kind of organisms to live and others not to. That's going to then have impacts. So all those things can get incorporated into our GCMs. So GCMs are, again, so complex that you're not going to run one on your computer. You're just going to be able to look at the results that other people have gotten by running them on these massive supercomputers that can do this enormous number of calculations, because we're looking at all these different interactions between all these little voxels across all these different processes that we're talking about here. But you can run some simple emix just in your browser, and you're going to be doing that in your activity for this unit. Okay, so then what happens when we try to check how well our models have done? Right, so we talked about hindcasting, where we calibrate our model by looking at how well it predicts the past, and then if it looks pretty good, we use it to project the future. So have our climate models stood up as the future has become the present, and we've gotten actual data to compare to predictions that we had from models? What we find is that our models have generally done quite well. So the graphic there shows a comparison of projections from a paper published in 1988 versus observed temperatures since that point. So this was a very famous, very important paper, one of the first papers to make big projections using climate models for the future. And so this paper was published in 1988, but it takes a while for papers to get published. So their starting point, the last year of data that these authors had when they ran their models, was in 1984. So they were basically saying, based on all the data up until 1984, we've developed this model that seems to work good if we do some hindcasting. So now let's forecast using this model and try to predict what's going to happen in future with future climate change. And you can see they've got a range of scenarios, right? They envisioned scenarios where we had big increases in greenhouse gases, ones where you had smaller increases, ones that were business as usual, where we basically didn't do anything different and just society kept on keeping on. So they made these projections, and then we can compare them to our actual data. So on the graph there, that's the black, purple, and dark blue lines are some of those different data sets of global surface temperature anomaly. And when you compare them to the green, the red, and the light blue scenarios from that paper from 1988, you can see that we were staying basically within the range of those scenarios, that our current temperatures are more or less in line with that scenario B, the middle scenario from this paper from 1988. And so this was, as I said, just the beginning of the development of our current general circulation models. So these are some pretty old models, but you can see even back in 1988, the models were good enough that they have relatively successfully predicted what would happen with global temperatures since that point, now that we have several decades worth of actual observations to compare to those old model runs. Now, there are a subset of models that have tended to overestimate temperature increases by a small amount. You can actually see the scenario A from the Hansen paper there, was overestimating things a bit. There are some models that will overestimate a little bit, but that's kind of a known thing in climate modeling, because in general, most of our models are pretty well on with what ends up actually happening. So that gives us additional confidence that we're on the right track, that our global circulation models are telling us something useful and important about future temperatures.